Hi girls, this lesson is going through transforming graphs and all the different types of transformations you can do. Okay, so far we've looked at these types of graphs in the table here. And so now we're going to see what happens when we do transformations to them. So we can do translations, so where you move something to the right or left or up or down. We can stretch the graph and we can reflect the graph along the x or y axis. So we'll consider this sort of thing, fx plus b, what that does, and f of x minus a or f of x plus a, fx times by p, what does that do? And f of q times x, and negative f of x, and f of negative x. So let's have a look at what happens there. Now, when we perform a transformation on a function, a point which does not move is called an invariant point. Okay, so first of all, we just want to do a bit of algebra and make sure we understand what all these are. So it says if fx equals x squared, find in simplest form, the first one is f of 2x. So you have to remember that we then need to square all of 2x, because 2x goes where the x is. So it's 2x all squared, which is 4x squared. B is f of x on 3, which equals, again, we put all of this where x is. So it becomes x on 3 all squared, or in other words, x squared on 9. For C, 2 of fx plus 1 equals 2 times what fx is x squared, and then just plus 1. And there's nothing to simplify there because they're not like terms. And for D, f of x plus 3 minus 4. Okay, so that means we put x plus 3 where x is again. So we get x plus 3 squared, but at the end we just minus 4. So the minus 4 part is outside the function because it's outside of those brackets. So then I get x squared plus 6x plus 9, and then minus 4, which becomes x squared plus 6x plus 5. Okay, so if you want to practice that specific idea, you can do some questions of exercise 5b. But now we're going to look at translations. Okay, so explain how the graph of y equals x squared is translated when converted to the following function. Okay, so we've got y equals x squared, and we want to know what happens to get from y equals x squared to y equals x squared plus 4. So we only need to explain it, but I do want to draw a diagram just to explain it to you, that y of x squared is a parabola down here. Hopefully you realize y equals x squared plus 4. If you were to graph or plot all the points, you would get a similar parabola, but just shifted up to 4 on the y-axis. So the vertex goes from at 0, 0 to 0, 4. So basically the only difference is y equals x squared gets shifted or translated upwards by 4 units. That's all that happens here. Now, the next one. It says y equals x minus 3 squared. So once again, here's the original y equals x squared parabola. So the question is, what does y equals x minus 3 all squared look like? Now, it's often wondered why. You hopefully know that we move it to the right to where positive 3 is and draw it there. But why do we do that? That's because, now, think about it this way. Look at the vertex of y equals x squared. That's when the y value is 0. So I want to know, in my new function, when is y 0? Which is at the vertex. So when y is 0, I would get x minus 3 all squared equals 0. If you square root both sides to solve the equation, you get x minus 3 equals 0 because the square root of 0 is 0, and these cancel out. And then you get, add 3 to both sides, x is 3. So that means the vertex happens when x is 3, not negative 3, but 3. So if y is 0 and x is 3, the point 3, 0 is on the parabola y equals x minus 3 all squared. So that's why we moved to positive 3 and not negative 3. So my new parabola is the same shape, but it's shifted to the right by 3. And hopefully you also know if I had y equals x plus 3 all squared, it would be shifted to the left 3 units. So I haven't actually answered the question. I need to explain what happens. So the explanation is y equals x squared shifts 3 units to the right. Okay, so basically here's a summary. If you have fx plus b, it moves vertically through b units. If b is a positive number, it moves b units upwards. If b is a negative number, it moves b units downwards. So for instance, if we had y equals x squared minus 8, since b is negative, we'd move downwards 8 units. For the next one, f of x minus a. Now, it says if a is positive, that means we'll have a positive number, so negative a. So that would still be, like y equals x minus 3 squared. I know it says a is positive, but they're considering a to be 3, not negative 3. So it would still move to the right. Over here, when a is negative, that's like when y equals x minus negative a or 3, which is y equals x plus 3 squared, which is why we do actually move to the left. You may not remember it like that. Just stick to your change the sign. Just go in the opposite direction. Now, for y equals f of x minus a and plus b. So now we're doing both. We're doing the fx minus a and the plus b like this. So the graph is translated horizontally a units and vertically b units. And we can say it's translated by the vector ab, which is good now because you've done vectors. So in other words, I'll do an example of that. So if we say translate y equals x squared by the vector, let's say 4 and negative 2, what does that mean? Well, remember, the x component is the top and the y component is the 0. So the x is positive. So we're moving, so that would mean we're moving to the right 4 units. But the y is negative, so we move down 2 units. That's what that describes. And you can write the function as x minus 4 all squared, because remember you have to change the sign. It was because this is positive 4, we have to have negative 4 in here. And then you just minus 2, because remember this is the same sign. This it doesn't change sign for the y part, for the outside part. Okay, so that's the function, and that's the description of a translation through this vector for y equals x squared. Now all of that is exercise 5C, so you can practice what you've learnt in exercise 5C. But now I'm going to go to stretches. Okay. Explain how the graph of y equals x squared is translated when converted to the following functions. Okay, so here y equals 5x squared. Now let me explain how this works. Let's draw big axes. And let's go 1, 2, 3. And here I'm going to go up by 3s. So I'm going to go 3, 6, 9. Okay, now I want to show you what would y equals x squared look like. Well, at 0, 0 squared is 0, 1 squared is 1, which is around here, 2 squared is 4, and 3 squared is 9. So it would look, y equals x squared would look something like this, and it's symmetrical, so I should do about the same shape on this side as well. So this black one here is y equals x squared. So what's y equals 5x squared? Well, 5 times 0 squared is still 0. 5 times 1 squared is 5, so we're up here. 5 times 2 squared is 20. Now we've gone very high. So look at that. Look how much steeper this one is, okay? And so it's symmetrical, so it looks something like this. And that's y equals 5x squared. Oops, sorry. So clearly, that multiplying the outside by 5 is clearly stretching the parabola vertically, which also makes it thinner. So let's write that down. So y equals 5x squared stretches y equals x squared vertically, making the function a lot thinner. It's thinner because it's rising quicker. So we get to higher values very quickly, whereas this took a bit longer. Okay, next one, x squared over 4. So now I'm going to look at y is x squared on 4. Let's try to use the same graph. So you can also think of this as a quarter times x squared. So let's see what happens. So we're timesing x squared again, but by a small number, a number less than 1. So let's think about that. When x is 1, 1 squared is 1. A quarter times 1 is a quarter. So that means we're really tiny. Then when x is 2, 2 squared is 4. A quarter times 4 is 1. So we're somewhere down here. Next, when x is 3, 3 squared is 9. A quarter times 9 is about 1.25. So we're only rising a tiny little bit. So look how fat or wide our parabola is. And it'll do the same thing on this side. So that there is y equals x squared on 4. So this one, it stretches the curve but horizontally, or it flattens the curve vertically, if you like. You could even say it flattens. Oops. Y equals x squared vertically. So it makes the function wider. Okay. Lastly, y equals x on 4 all squared. So now we're squaring the 4 as well as the x. So I'm going to use red color. Okay, so let's have a look at this one. When x is 1, you get 1 over 4, and then square that, you get 1 on 16. That's so tiny I can barely draw it. That's even lower than the green. So when x is 2, we get 2 over 4, which is a half. A half squared is a quarter, so that's like down here somewhere. When x is 3, we get 3 on 4, and then square it, 9 on 16. So that's not even 1 yet. It's still really low. How about when x is 4? 4 over 4 is 1, 1 squared is 1, so finally we're at least at 1. So we are even wider than the green one. We're like out here somewhere. So that's even wider than before. So in this case, now I want you to think about the difference here. This 4 is being applied to x. Therefore, it's going to have a horizontal, because the x-axis is horizontal, so it's going to have a horizontal effect. So what we say here is this graph stretches the function of y equals x squared, I should say, horizontally. Now, why didn't we say that before? We said it was a vertical thing. We said over here it flattens it vertically. That's because we're dividing the entire function of x squared, or y equals x squared, by 4. Whereas here we're only dividing x by 4. Therefore, that's why we think of this as a vertical transformation, and we think of this as a horizontal transformation. But if you're ever not sure, you can always plot points, or often in IB tests you're given a graph and say, perform this translation on it. You can even use values from the graph and try and find the new values. This makes a wider function. Now I'd like to do one more. What if it was, let's call this d, y equals 2x all squared. Now that means, for instance, if we have 2 times 1 or 2 times 0, that's just 0, and 0 squared is 0. 2 times 1 is 2, 2 squared is 4, so that's up here. 2 2s are 4, 4 squared is 16, so all of a sudden I'm very big, so I'm up here somewhere. So this one's quite steep in comparison to y equals x squared over here. So what I want you to realize that this actually squishes the graph horizontally. So it actually makes it thinner. So you've got to think of it like, because I'm timesing the x by 2 on the inside, it's a vertical shift. So we're squishing it horizontal. Sorry, I apologize, I said that wrong. It's a horizontal shift or effect. So we're squishing the graph horizontally. So this graph squishes, or maybe there's a better word, I'm sure, sort of squashes the graph horizontally. Horizontally, making the function thinner. So basically, after all that, the summary is here. For y equals p times fx, so in other words, I'm multiplying the entire function by p. If p is bigger than 0, we get vertically stretch the graph by a scale factor of p, so that if p is bigger than 1, that makes it steeper. So this says further away from the x-axis. In other words, it makes it steeper. But if p is like less than 1 or bigger than 0, like a quarter or something like that, here, it moves closer to the x-axis, or in other words, it makes it wider. For y equals f of qx, so q now is multiplying x, not the function, but the x value, and then the function is being applied. So we horizontally stretch the graph by a scale factor of 1 on q. Now that sounds weird, but look at this, back at this one. Here. This is like qx, where q is 2. And look at the corresponding function. It made it thinner, so the x values became smaller. So it multiplied the x values of the original function, which is this one, by like 1 on 2, so it halved them. So for instance, this value got moved to half of that, which is, sorry, the x value of 2 got moved to half of that, which is at 1. This value got halved, which is about here. So it's moving inwards, which makes it steeper. Now, if q is bigger than 1, it moves closer to the y-axis, and that again becomes steeper, like in the one of y equals 2x all squared. If q is between 0 and 1, like in this one up here, where x on 4, where so q would be 1 on 4, and when q was 1 on 4, we got this, we got this wider graph. So it's further away from the y-axis, or in other words, wider. So hopefully that makes sense. And now you can look at exercise 5D for that in more detail. Now we're going to look at reflections. Okay, so here we got y equals negative x cubed. If you don't mind, I'm going to change it. I'm going to change the function to x cubed plus 1. So y equals x cubed plus 1. So now I want to negate all of that. So I'm going to get negative x cubed plus 1, or in other words, negative x cubed minus 1. So what happens there? Okay, let's think about the function y equals x cubed plus 1, the original function. So I might put a few values, 1, 2, and 3, negative 1, negative 2, negative 3. Okay, and let's go up by 2's, maybe 2, 4, 6, 8, negative 2, negative 4, negative 6, negative 8. Okay, so for y equals x cubed plus 1, when x is 0, you get 0 plus 1 is 1. When x is 1, you get 1 plus 1 is 2. When x is 2, 2 cubed is 8, plus 1 is 9, so we're about up there. Now, what about when x is negative 1? Negative 1 all cubed is negative 1, plus 1 is 0. Negative 2 all cubed is negative 8, plus 1 is negative 7. So I'm around here. So what I've got happening is this kind of shape. And this is what a cubic looks like. So that's y equals x cubed plus 1. That's our original function. Let's see how it changes when we negate the entire function. So put the negative on the outside of the entire function. Let's do this one in blue. So what do we get? Well, you can use either this one or this one. They're the same. So I'm going to use this one over here because I think it's easier. Negative 0 is 0. Minus 1 is negative 1. For x is 1, negative 1 minus 1 is negative 2. When x is 2, negative 2 cubed is negative 8. Minus 1 is negative 9. So this time I'm down here. Now let's go to negative 1. Negative 1 all cubed. Well, negative 1 cubed, so I might write this out. So negative 1 cubed minus 1 equals negative. Now negative 1 cubed is negative 1. So what's a negative 1? The two negatives make a plus, so that just becomes 1. Then you got minus 1, which is 0. So you get 0 here. Then negative 2 cubed minus 1, when x is negative 2, is negative 8 minus 1. That there becomes positive 8 minus 1, which is 7. So I end up here somewhere. So look at what's happening. That is y equals negative x cubed plus 1. that's when we negate the whole function. And what happened? It looks like it's been flipped down that way. In other words, across the x-axis, it's been flipped. Okay, so for A, the graph flips. So the graph, I mean this function here, flips or reflects, I probably should say, y equals x cubed plus 1 along the x-axis. Now for B, what I want to do in B is I'm just negating the x part, so the plus 1 stays the same. So that's my whole function. So I'm just going to take away this now. Okay, now I'm going to use green to graph this new one. So looking at this function here, we're going to graph it. So when x is 0, you get negative 0, which is 0, cube that, still 0, plus 1, we get here. When x is 1, you get negative 1 cubed, which is negative 1, plus 1, which is 0. When x is 2, negative 2 cubed is negative 8, plus 1 is negative 7. Okay. Now, what I might do now is rub out the blue just to help you see everything a bit clearer. So we're just comparing our original function with the original with the new one, B. Okay, so we've got this kind of shape happening. Now let's put negative 1 in. Negative 1 is positive 1. Cubed is just 1. Plus 1 is 2. Negative 2, so when x equals negative 2, you get positive 2 cubed is 8, plus 1 is 9, so it's up here somewhere. So we've got this happening. So what's happened? It looks to me like the function y equals x cubed plus 1 has flipped again, but this time along the y-axis. So for B, the graph flips y equals x cubed, or reflects it, along the x-axis. So for y equals negative fx, so notice the negative is outside f. So it's kind of like we're negating y since fx is like y. So since we're negating y, the function gets reflected along the x-axis because the positive y's become negative and the negative y's become positive. So it flips across the x-axis. For y equals f of negative x, notice there that the negative is being applied to x. So it's the x values this time that switch. So we're reflecting along the y-axis. So that all corresponds to exercise 5D. Have a go at looking at that and doing some questions. Okay, thank you.